This class we study wave. Wave. So we know what wave is. Wave. Wave has oscillating behavior and in in two viewpoints. In time, a medium, a point in the medium moves up and down. It's a kind of oscillation. Sure, it is a for a transverse wave, it is moving up and down. A longitudinal wave, it is moving left and right. Uh, if we choose this is the direction of the wave propagation. In addition, in the x space, the position space, it has oscillating behavior up and down when we move to the right and left along the direction of wave propagation. So we know a harmonic oscillator has an equation of motion, and its solution is sine omega 0 t minus delta. It is the phase constant, and we have amplitude. This is the solution for a simple harmonic oscillator. And actually, a wave can be understood as a collection of many, many harmonic oscillators that has different phase constant. For example, we have an array of points that are connected in series with the identical springs. If we apply some perturbation, at some point and release these points, and then oscillation begins, and each point oscillates as time goes on, and this shape of wave propagates something like that as time goes on. So what we want to do in this class is to understand the wave as a collection of harmonic oscillators, and the phase for every part of this wave, which is called medium, has a slight difference between two adjacent points. It's varying in this way. So this delta is not a constant in the collective way. This can be understood as, for example, xk of t is a k means first, second, third, fourth ID number until the nth particle, and k dependence appears something like minus something k. K is a spatial component the integer identifier identifying the spatial position. For example, x of k is d times k, something like that, where d is the spacing of adjacent points, massive points. So what we would like to do is to understand the argument of sine function. Basically, the wave in the t space is a sine wave, and sine wave, and in the x space is again sine wave. So at the end of the day, we will find that it is a sine something like kx minus omega t, or some function of x minus vt style. So this is what we are planning to do to understand a wave as a collection of harmonic oscillators, and the solution will be like omega t minus delta, but this delta depends on the position. This is only a single particle oscillator, but what we want to do is to analyze the wave as a collection of particles that are attached to specific spring with the spring constants. So this is our plan to attack this problem. So anyway, wave is not a particle. It's not a single particle. It's a fluctuation of medium, and medium oscillates the elements of medium. For example, water, air that transmits the sound, so or vibrating string that generates a sound. They are collection of oscillators. For a single oscillator, we have introduced X, but many oscillators we introduced X3, X4 until X to the n. When we have n oscillators, we have many coordinates. And this is discrete coordinates, so this is a kind of sequence. So we have n element sequence that represents a deviation from some equilibrium position for each oscillator. Okay, and then just like what we use for vector, we use x1, x2, x3 as Cartesian coordinates. We list everything as a coordinate, which is a not xyz coordinate, but independent coordinates. We say it is a generalized coordinates. Let me call x1 through xn. And what we want to do is to find out the equation of motion for not a single position vector, but the collection of position vectors for every oscillator. So this list becomes an n-dimensional Euclidean space, and we'd like to increase the number of particles to make a continuum limit, to take the continuum limit to consider actual wave propagation. So beginning point is to list sequence of positions, each of which identifies the position vector of a single oscillator, and the collection of them is represents the whole shape of wave. And this is a function of every component is a function of time. And when you move from the left to the right, these represent the position of each oscillator. Okay, so there is both the time dependence and spatial dependence and time dependence for every oscillator. So when we increase the number of particles, then these points sequences are dense enough dense enough as n goes to infinity to make a curve. Then this one can be transformed into a kind of function that depends both on time and space. So this one we call wave function. And at each time and position, and each time and position, this wave function represents the deviation from the equilibrium position of each oscillator that is placed at every point x. Okay, so wave is not a particle, but a collection of particles. That's the beginning point of our analysis. This is a simple example of wave. Blue wave propagates from the left to the right, and red one, and blue wave propagates from the right to the left. In the meantime, they approach together, and at this point, they make a complete overlap. That means blue one and red one, they are equal at this point, and it is doubled to make a resultant wave. The reason is that the two waves denotes of psi 1 and psi 2 denotes the deviation from the equilibrium position that is flat in this case, and deviation will be added because the deviation is just a displacement, and displacement is a vector. Any vector, we have a vector A and vector B that can be added algebraically for each component, A1, B1, comma, A2, B2, comma, A3, B3. They are added algebraically, something like that. In the case of the collision of two particles, when they collide, when they meet, they bounce unless it is a penetrable. Penetrable particle doesn't exist at all. So it bounces back. There is a strong potential to resist the force that against any other thing. Sometimes collapse, but mostly they bounce. This is different because they do not have any potential. It is just a displacement, and the displacement are simply added. Okay, so the wave is quite different from the particle. So particle cannot, it is impossible to have these two particles placed at a single place because a particle is assumed to have a very hard space, assumed to be very small, tiny one. However, they have its own structure, and it won't be broken. But wave is not a particle, it is just a displacement, and displacements can be added algebraically. That's quite different. Particle itself is, the reason, another reason why they add is this single particle, every single particle do not move. It is just oscillates at the same place, and it is impossible to overlap each particle. The two particles do not meet again, and the wave is just transmitting the energy to that particle to shift, to make another shift, something like that. So this is not a collision of particles, it is just addition of displacement. That's the reason why wave function adds together. Okay, so what we want to do is next to find out the equation of motion to describe the wave. So how they propagate from some place to another. So shape, this displacement is transmitted to another particle, but this particle does not move. It is oscillating at at the same place, the same place. Okay. So we are more close to the uh, our actual analysis based on this many body theory. Again, a system of weakly bounded and simple harmonic oscillators. We have masses. They do not move very far to touch the nearest neighbor. They are just oscillating in this direction or either or this, and the energy is transferred to nearest neighbors. And in the global, the macroscopic scale, they have some wave structure. Anyway, wave propagates along a direction. This is V, and relative to this direction, we can we can distinguish the difference between the oscillation along this direction and that direction. This direction that is parallel to the wave propagation is called longitudinal direction. So such kind of wave that oscillates along the direction of wave propagation is called longitudinal wave. And another wave that propagates vertically, perpendicularly to the direction of propagation, just like a vibrating string, up and down, it is called transverse. This direction is called the transverse, and this wave is called transverse wave. So this is an explicit illustration for the transverse wave. Wave propagates in this direction and fluctuation is perpendicular to the direction of propagation. So transverse wave. Longitudinal wave, the density changes because along this direction. For example, for the sound wave is a longitudinal wave. The oscillation is a parallel to the direction of propagation. In nature, there are three kinds of waves. Until now, we have discussed the mechanical waves, vibrating string and propagating sound wave in the air, something like that. There is another wave that is electromagnetic wave. Without electromagnetic wave, our life is very inconvenient. We cannot use cell phone, we cannot watch TV. So electromagnetic wave, a very special wave, and contemporary life is stick to this electromagnetic wave. Electromagnetic wave is always transverse, and in addition, if we compare, in comparison with the mechanical waves, mechanical wave has always medium. Without medium, mechanical wave cannot propagate. However, electromagnetic wave can propagate in vacuum. For example, the sunlight travels the vacuum to arrive at the earth. There is no medium, nothing. It is a vacuum, nothing. And it propagates in the transverse direction. Anyway, electromagnetic wave has a special nature. It is propagating in vacuum. And in addition, the electromagnetic wave always travel with the speed of light. In the vacuum, this is a speed of light in the vacuum. it can also travel through the medium, and it changes. Index of refraction is known, then it slows down with the c over n. Anyway, this is a very special wave. And another way is a particle itself is behaving like a wave. Very strange, but it is the fact. Elementary particles, if you study elementary particles such as electron or proton or subatomic particles, they are always wavy. They have they have their own wave mechanics. So it looks strange, but more than now the 100 years we know that it's a fact, and we are using quantum mechanics quite very much. And your computer is impossible if without understanding quantum mechanics, such kind of appliances cannot be built and used. Okay, let us seriously consider n-dimensional harmonic oscillator. What I'd like to do is not to solve this problem, but to copy the result and the solution, and the solution derivation of the solution can be found in the KPOPE guide for classical mechanics, CM 25 through 27. I do not want to uh, explain every detail of it in this class, but anyway, from elementary school or high school, you already have learned about the harmonics of musical instruments, a pipe or vibrating string, and you never know why, but you are able to compute the harmonics. For example, vibrating string vibrates. This is the fundamental mode, and the first excited state vibrates like that. You know, you know the answer. Although you do not know why is the answer, but you can understand why if you read it through, if you have enough time and you are curious about why. But let me copy this result. This fundamental mode for the vibrating string is the case r equals 1. And when you substitute r equals 1 and n is very large, and this is a very tiny number because n goes to infinity, for example, tiny number, then sine tiny number is approximately that number if you neglect higher order pieces. Remove anything. In that case, this is angular frequency of this fundamental mode. W1 is square root tau md. M is a mass of each massive bead, and d is the spacing, and tau is the tension of the string. And multiplied by this one is pi. I substitute r equals 1 and 2n plus 1. This is the frequency, fundamental frequency, 2 pi f, fundamental frequency. Okay? All right. And then, first excited state, so second harmonic, that is the case for r equals 2. So, again, it is a small number. Then next frequency is just 2 times omega 1. And the third one, again, it is a small. 3 times omega 1. So n times omega 1 is nth harmonic. However, it is not always true. You will notice that when n is very large, and if you will find the maximum value at n equals r equals n. In that case, it is approximately sine n pi to n plus 1 pi. So it cancels in the limit n goes to infinity. Is sine half of pi is approximately 1. So there is a frequency, maximum frequency. There is cutoff frequency. It cannot go further. It has a maximum value. Although this series omega n times omega was found and guessed by Pythagoras, and they were wrong, and the actual result is not increasing linearly, but it is increasing. It is a sine wave. It approaches the maximum value, that is the frequency cutoff at this value, because at large n it becomes 1. So anyway, this one explicitly shows that this is a monotonically increasing function. Although that has a maximum, there are n independent different frequencies for the vibration. That means 1, 2, 3, 4. That means any vibration of a string is a sum of these harmonics with the specific frequencies. Okay? And then for a given frequency, there is a specific spatial components. What it is? What is it? R equals 1. This looks very complicated, but not so much complicated. R equals 1 if you substitute. So sine n plus 1 pi through sine n plus 1 n pi. Why don't you take n goes to infinity? It is a 0, and it is also 0, right? N over n plus 1 equals 1. So sine pi and sine 0. That means in between, it is just this one. Not a sine function, but points of sine function. All right? When r equals 2, then it is something like that. Now you know why they drew this is fundamental and next one and next to next and so on. But because this was the answer, they didn't tell you the answer exactly, but this is the exact answer. We will show why this is the answer. We will construct the equation of motion for the vibrating string. And if you substitute these results into the equation of motion, you will find it is true. It satisfies F equals ma, Newtonian mechanics exactly. Now we call this vector, this is the distribution over space. This is the sequence. Position 1, 2, 3, 4, 5 until the nth bead on a string. So these are just like Cartesian components x1, x2, and x3 for a three-dimensional vector. So we call this one characteristic vector, that is eigenvector. This eigenvector corresponds to Nth harmonic. Okay, and this is a frequency. This distribution of points, this kind of one or this kind of one, this kind of one, they are specific for a single frequency. Okay? And then this is the eigenvector distribution in the space, and each of them oscillates. But for this distribution that is called R equals 1, there is a specific frequency omega 1. So for omega 1, for example, this 1, I should have written this I with R. Let me correct this. Here I have corrected the typo. The frequency is given in here, and we know the answer completely. The free parameter is amplitude and phase. That phase is completely determined. Oh, this is AR cosine, and this should be psi. I should correct it again. Okay, I have corrected this as a sine, but because of the boundary condition, it is fixed at the end. So this one vanishes, only sine contribution survives for the vibrating string whose two ends are fixed. In case it's a pipe, the vibration of the air inside the pipe, then the displacement in here is maximized. For example, this is cosine survives and sine disappears. All right. Now we have found the eigenvector that is a sequence from the k equals 1 to n, and there's an n plus 1 at the endpoints at x equals L, and k equals 0, the other endpoint at x equals 0. So although it is a sequence, if we take the limit n goes to infinity, they are well connected, and we can consider a continuous function. So with psi r consists of n elements, psi r1 through psi rn, capital N. And if we increase the number of elements, and then n goes to infinity, and we can connect everything all together. And this column vector can be expressed as a function, where x is the coordinate, continuous coordinate of each oscillator. And when we define x continuous variable, it is because the spacing is d, the position at some point is the kth element, first, second, third, and the kth element has the position. Because the spacing is d, the xk equals k times d, and d is total length divided by number of beans. Because there are n beads, there are n plus 1 spacing. So because of this, we can replace this sequence of the position as a continuous variable. And after that, we find this is the wave function. This is an eigenvector, and this is an eigenfunction. And any wave function is a linear combination of eigenfunction. just like what we have done with the harmonic oscillator, we found two eigenfunctions, and the solution is a linear combination of these eigenfunctions. Just like that, we have n oscillators, n eigenfunctions, and full wave function is a linear combination of all of these eigenfunctions. So this is the case for the finite n case. Number of b's are finite. This n equals 5. And this blue curve is the exact eigenfunction as n goes to infinity. So there is an exact match. This is this wave function. So eigenvector, the finite one, we use eigenvectors. We have n element column. N equals r equals 1, fundamental, r equals 2, and so on. And they are in the lowest lying frequencies, they are integral multiple of the fundamental frequency. And as n goes to infinity, well before infinity, this is just 100. This looks very continuous function, and it exactly matches with the H fundamental harmonic and the harmonics. When we expressed a vector in a Euclidean space in 3 dimensions, we introduced Cartesian basis vector and used these vectors. We expanded that. So this is equivalent to the fact that identity operator is E1 cross E1, that is a direct product, E2 cross E2, and E3 cross E3. In the matrix form, it is a row vector, column vector, row vector. 0, 0, 1, 0, 0, and this one is a 0, 1, 0, direct product, and this one is 0, 0, 1, direct product, 0, 0, 1. Then any 3-dimensional vector can be expressed, expanded in this form. Nothing is missing. So it is called a completeness relation in the Euclidean 3-dimensional vector space. The similar completeness relation exists for this normal modes of n oscillators. Any oscillation of collective behavior of n oscillators are described in terms of eigenvectors. We have found that there are omega r frequency that has its own eigenvector, and this eigenvector is just like the unit Cartesian basis vector. Therefore, it is this kind of, what's that? This is a projection of eigenvector onto the state R. R runs from 1 to n. And if we project this out, what we find is that there is a complete time dependence is factored out, as this is called, this is a coordinate, Cartesian coordinate or component, and this is a normal component or normal coordinate. And this is an eigenvector. So completely any oscillation of n oscillators is expressed as a linear combination of n independent oscillators with distinct frequency. and this is called eigenvector. And as n goes to infinity, this eigenvector is to be transformed with the eigenfunction. This kind of space is called the three-dimensional Euclidean space, and this kind of space is called the n-dimensional Hilbert space. Hilbert space. And again, the expansion with respect to this frequency mode and the solutions for the normal coordinate is that another basis for the Fourier expansion. Let us consider the definition of wave. Wave is propagating distribution of oscillations inside for the many oscillators hidden in a medium. So we first consider the case, the simplest case, the shape of a wave translates as time goes on with the propagation velocity. In that case, this function, this is a wave function, is translating, and this distance of travel was velocity times time. What we want to do next is to find out the equation to describe this kind of motion for a wave. So wave function's equation is called wave equation. That's what we are looking for. This is a wave equation. Important point is that the wave function has an argument x minus 3t. Here, the shape of the function is the same, except that it has been translated along the x-axis or n hat axis. Then what we want to do is just to subtract that amount of translation. Therefore, if I take the derivative with respect to t, I obtain the derivative of this function. However, because of the chain rule, I have additional factor, that is minus v, for a single time derivative. And for the spatial derivative, I also have the same kind of derivative, but I have a direction. If I take the time derivative twice, what I obtain is a v squared. If I take the spatial derivative twice, that is Laplacian, then I would get n hat squared. N squared, that is the unit vector along the propagation direction, and it is 1. So they are identical except that there is additional factor of velocity squared for the double time derivative. As a result, if I divide both sides by v squared, this one cancels, and right-hand side exactly the same. So I can construct the equation of motion for a wave. If I subtract these, the difference of these must be 0 always. Therefore, this is the wave equation. This is the wave equation. The partial wave expansion is, we remember the displacements Q for n oscillators were expanded in as a sum of column vectors called eigenvectors. Eigenvector, which we call psi r. eigenvector, and it's a coefficient. It does not have any time dependence, and the time dependence is factored out as a coefficient, and that was called the normal coordinate. And sum over R and oscillators. In terms of these eigenvectors, it is expanded. It is a kind of Hilbert space, and in terms of this coefficient, it is expandable in WR and omega R. That is the frequency. So we say it is a frequency space. In the frequency space, we find for small r, omega r was multiples of fundamental frequency. This kind of expansion is called Fourier expansion. So Fourier expansion considers the result is the same. Fourier expansion considers the series expansion in terms of the normal modes. In the limit of a continuum limit, we take the limit n goes to infinity and the spacing goes to 0. In that case, we have the eigenvector is replaced with eigenfunction with the subscript r represent the frequency, and this column vectors of first, second, third elements, these finite elements, is to be replaced with continuous variable and continuous function. And these coordinates are to be replaced with wave function that depends on both time and space. So for the continuous variable, continuous wave function, we call it is a Fourier transform. And for discrete summation, we use Fourier expansion. Let's see. At some point, at a fixed time, we can take a picture of a wave, and this one shows the Fourier expansion in Hilbert space. This arbitrary function is an element of the Hilbert space, means it is expandable in series of normal modes. And normal modes has, at lower frequencies, we learned that omega r is proportional to the fundamental frequency. So the next one is 2 times omega 1, 3 times omega 1, and so on. Something like that. This is also true for the wave number in the shape in X space. This is the frequencies for the T space, time space. In the space for the space, still the distribution eigenvector looks like that, right? Both the frequency and the wave number space, the spatial dimensions. So it is psi 1 and psi 2, psi 3. Okay. So this kind of expansion completely reproduces arbitrary oscillation in a vibrating string. Any vibration in a string can be expressed in terms of this series. This is called the Fourier expansion. The good point in here is the series is a function of series. This is a function. but they have a different arguments. Okay? Just like what we usually do for the Taylor series expansion, it is polynomial. All functions, this is a series of functions, right? Function sequence are summed to have a series. They are matched to, they approach. It is not exactly the same, but if you sum to the infinity, it approaches the exponential x. The same is true in this case in Fourier expansion, Taylor series expansion. Both of them are expansion to reproduce the original function in terms of a very easy to deal with function. And because the basis functions for this Fourier expansion is a sinusoidal function, so we usually study the sinusoidal function. That is, it is natural to study sinusoidal function for any wave function. And in the space, in spatial dimension and time dimension, periodicity is true for both. So it's a period in space is a wavelength, period in time is a period, and angular frequency is a 2 pi over period. The 2 pi over spatial period is called wave number. And velocity is a wavelength over period, and the wavelength is written in this form. This is omega, and this is 1 over k. So omega over k is the velocity of the wave. In the continuum limit, we take n goes to infinity, m goes to 0, d goes to 0, but keeping the density is the same, okay, constant, and length is L still L, mass is still m. Now let us look for the equation of motion for every bead. There is rth bead and r plus 1th bead and r minus 1th bead, and r goes to 0, 1 to n. Okay? I'd like to know the mass. This is mass. I'd like to know the position, psi of r. I'd like to know the acceleration, double time derivative. Because there are r in the continuum limit, r is transformed into x variable. R times d equals xr, and I'd like to make a transformation to a real number. So it is a derivative specifically for the time only. So double time derivative. It is to be replaced with double time derivative. So I have f equals ma. What is f? Tension is f. And the horizontal direction, I exaggerated to have a large angle, but it is assumed to be very small. Then horizontal force cancels. These two tensions cancel in the horizontal direction. In vertical direction, it's going up. So the magnitude is tau sine theta. And here, again, tau sine theta, but it is to the left. It is downward. So it is upward. So I add this one. R plus 1 applies this one. And the force is a plus tau sine r. And what is sine r? This is psi r. This is psi r plus 1. The difference is psi r plus 1 minus psi r. and the width is d. And for small theta, d is almost same as d. So this one over d is sine theta. And I can use this one. I can substitute this one. Finally, this one is this, and this one, psi alpha sun, flip the order, then you obtain the negative side. Okay. We notice that the difference psi r plus 1 minus ir is actually psi of x plus d minus psi of x, something like that. So if I divide it by d, it is a partial derivative with respect to x. And then, so this becomes a partial derivative of x if we include this d. If I include another d, this partial derivatives a difference over d is a double partial derivative with respect to x. Okay, that's the reason why I have additional factor in the numerator. I have to divide d one more and multiply d. Okay. All right. And this d is replaced with dx. So differential d is replaced with dx. So it's fine with dx, and we can still erase it and just the d. That's fine. Finally, this is left-hand side has a double time derivative. Right-hand side is a double spatial derivative. Okay, and I have canceled the d both sides, and then this tension is to be multiplied in here. So let's see. So m over d is rho. That's the reason why this one appears here. And the rho over tau appears. This is a wave equation. When we replace rho over tau is 1 over v squared. Wave equation. We have shown that the vibrating string carries the wave, satisfying the wave equation. That's it. So this is the summarized, we summarized everything together. We can also consider the potential energy. Potential energy is 1/2 kx squared style. So this tension gives us tension. Because of this tension, the tension T over D acts as a restoring force. So we can do the calculation for, because the force is given in here. We can integrate to find out the potential energy, and that potential energy is like that. So I include d in the denominator, and because the d has a single power, I put d twice and leave one factor of d, and this is 1/2 tangent, and this is the spatial derivative square, and d is actually dx, so we can make this is a kind of a Riemann sum. So potential energy is an integral from 0 to L of an integrand, and this integrand is called potential energy density function. If we integrate over 0 to L, it becomes potential energy. In a similar manner, I can compute the kinetic energy, there is a 1Fm x dot squared, from wave function. So this is velocity, and density times dx. Rho dx is a dm, mass. So 1/2 mv squared is integrated from 0 to L. This is called the kinetic energy density function. Density function is integrated to have kinetic energy. Potential energy density function, if you integrate, then you have potential energy. The sum of potential energy and kinetic energy is called total mechanical energy, or Hamiltonian. So after integrating the Hamiltonian density, that is kinetic energy density and potential energy density, this is the total mechanical energy of the vibrating string. So for a given wave, this kind of style, I can take the partial derivative for time and space, and I can compute the kinetic energy density function and potential energy density function. If I have a wave function in the sine form, fixed end vibration, then both of them are cosine squared. So if I add these two, I obtain the Hamiltonian, that is total mechanical energy, and that is depending on time. So I'd like to take the either time or spatial average, that is cosine square of average over period is always 1/2. So finally, I understand 1/2 rho omega squared a squared, this amplitude of original wave. This is the total mechanical energy of a vibrating string. It's very important. We have frequency squared, amplitude squared, and a density. This is a Hamiltonian density. Everything are all in phase. Okay, potential energy and total kinetic energy density, potential energy density, Hamiltonian density. And if you take the average, it is just 1/2. This kind of structure is exactly the same for electromagnetic wave. So in the next semester, when we learn electromagnetic wave propagation, the same logic it will be used. This is called the classical field theory. Okay, so in the self-test, we review what we have done in detail for as far as especially for the orthogonality of the wave eigen eigenvectors, and we take the limit and goes to infinity. We can make a transformation to construct eigenfunctions, and eigenfunctions are also shown to be orthogonal to it among one another. That's it for today. Thank you.